Hello everyone, welcome to my channel. In this video we will learn about the Huffman coding. So how can we solve the Huffman coding using the greedy method? Okay, so normally we know that whatever the data stored in the system or whatever the data that we are transmitting in the internet, so all the data will be in the compressed format. That means the text that we are typing will get converted into ASCII format. So ASCII is a 8-bit binary bit format, right? So whatever the data that we are transmitting through the network or the data that we are storing on the system will get stored in the format of binary bits. So a combination of zeros and ones in the system. Okay. So how we are compressing the data? So we are compressing the data based on the ASCII format. So ASCII format is a very well known format. So it can be easily decoded by any third person. Okay. So that's why if there is a chance of coding our encoding process of our own data by using our own format, then we can use the Huffman coding. So here there is no prescribed format, so we can do so we have the freedom to encode our own data using our own codes. Suppose we wish to save a text ASCII files on the disk or to transmit it through a network using an encoding scheme that minimizes the number of bits required. Without compression, characters are typically encoded by their ASCII codes with 8 bits per character. So we can do better if we have the freedom to design our own encoding. So this is the message that I want to transmit through the network, or this is the message I want to store on the disk. Then the ASCII of this message will be compressed with the data and stored on the disk. So the ASCII of the value B and the ASCII of C, so like that it will be stored on the system. But this ASCII format is very well known format, so that's why we are using here our own encoding format, that is called as a Huffman coding. So here we have two types of encoding formats, that is fixed size encoding and variable size encoding. So first of all we will take a look on fixed size encoding. So this is the fixed size encoding. So this is the message that I want to transmit through the network. So along with this message I am going to add the encoded bit table. So whatever the encoding that we are applying on the message, so the compressed form of the encoding, so that we are going to add with this message. So this is the character, this is the message that we want to transmit through the network. Okay. So here what are the different characters that we are using to transmit through the network? So A, B, C, D, E. So this is a combination of A, B, C, D and E, right? So what are the number of A's in the message? So 1, 2, 3. So 3 A's are there. Okay. So the characters are A, B, C, D and E. So what is the counting or frequency of the characters in the message? So A is occurring 3 times here. So 3. And how many times B is repeating here? 5 times. C 1, 2, 3, 4, 5, 6. So 6 times it is being repeated. And D 1, 2, 3, 4. So 4 times it is being repeated. And E is repeated here twice. So this is the count or frequency, that is number of times the characters are repeating in the message. Next we need to code. So we have to form the code. So normally the ASCII character A has 65. The ASCII value of A is 65. But we are not using the predefined format, right? So we are creating our own codes. Okay. So in generally, if you want to represent 5 bits of data, so how do we represent 2 bits of data? So 0, 0, 0, 1, 1, 0 and 1, 1. Similarly, how do we represent 3 bits of data? Suppose we are having here 2 square, right? So I want to represent 3 bits of data, so 2 cube, that is 8 times we can represent. So 0 0 0 0 0 1 and so on, triple 1. Okay, so here I have 5 characters here, A, B, C, D and E. So 5 characters I have to represent. Okay, so for representing 5 characters, so 2 cube, so 2 power 3 is enough. So 0 0 0 to triple 1. Okay, so we are coding this here like 0 0 0 0 1 0 1 0. So for C, 0 1 1 and E 1 0 0. So remaining 3 bits will be, we are leaving that one. Okay, so 5 bits we are using here, because if you use 2 square, 2 power 2, then it is not enough for the 5 characters. So now in order to transmit the message, we have to add the message and encrypted data also. So along with the message, we have to send the table where we are compressing the characters to a particular code. So we have to attach that coding also in the format of table to the message. So we have to transmit the message along with the table. Okay. So what are the fields in the table? So character, count and codes. So what are the number of characters here? 5. So totally there are 5 number of characters. And what are the total count here? So total count is 20. Okay. So now we need to attach all these details with the message, along with the message. Okay. So character is 5. So character we have 5. And each character has 8 bits. So 5 into ASCII value of the each character is 8 bits. So 5 into 8, that is 40 bits of data. And codes. Okay. So what are the number of codes here? So we have code for 5 characters. So 5 into, and each code is of length 3. So 5 into 3 is 15. So we have the character codes. So now, so we need to add the count value. Okay, so count value. So what is the count value here? 20. Okay, so 20. And each count is having the 3 bits of data. It is represented with 3, it is coded with 3 bits of binary bits of data. So 20 into 3 is equals to 60 bits of data. So if you add all these things, so we are going to, this is the total table length. So 40 plus 15, that is equal to 55 is the combination of characters and codes. 55 plus 60, that is equals to totally 115 bits. So we are adding, so 115 bits. So message is of 60 bits length. So this is the message, and the table length is 55. So table length is 55 and message length is 60. So totally we are transmitting 115 bits of data. So if you are transmitting only the, if you are transmitting the actual data, then it takes 160 bits of 160 KB. And suppose if you are transmitting the compressed version of the given message along with the coding format, along with the coding table, then it will consume 115 bits. So here we are saving up to 30 to 35% of transmission of the bits. Okay, so this is how the fixed size encoding is done. So here we have seen the fixed size encoding, right? So the code is, so the message is given, so we are having the fixed size encoding. So for not many times, every time the code may not be fixed size. So it may be sometimes variable time also. So if there is variable time of coding, then we will see how it will be. So here the table, the message form, the message is same, and so we are going to code it for the variable size. So in the case of the optimal merge pattern, how we have merged the numbers in the list. So similarly here we are going to merge the numbers in the given list. Okay, so first of all we will take the count value here. So we are writing it in the ascending order 2, 3, 4, 5, 6. So now we are going to merge these numbers. So 2 plus 3, so we are taking the first two minimum numbers 5, and the next two minimum numbers 5 plus 4, that equals to 9, and next two minimum numbers 5 plus 6 equals to 11. Okay, and then 9 and 11, so which is 20. Okay, so in this manner we have measured the count value here. Okay, so for encoding we need a message and table used for the encoding. So here we are going to represent the left child with 0 and the right side child with 1. So here the left child, so this is the left side, right? So 0, and the right child with 1. Similarly here left child with 0 and right one is 1. Okay, so now how we will code the values here. Okay, so here I want to code the count value 3. So 3 is given here, so we have to count it from top down approach. So 0, 0, 1. So 0, 0, 1 is the code of the 3, 0, 0, 1. And for 5, so 5 how we will calculate? 1, 0, 1, 0, and then for 6, 1, 1. So now for 4, how we will calculate? 0, 1, and for 2, so 3 will 0, 3 will 0. So this is how we will write the codes of the each count here. So now we will calculate the total here. So we have the characters are 5 bits, 5 characters, and each character carries 8 bits. So 5 into 8 is 40 bits. Okay, and total count is 20, and total codes. So what are the number of codes that we are sending? That is 12 bits. So here we are sending 12 bits of data. Okay. So how do we calculate the table bits? So table equals to character plus code. So what are the total number of character bits? 40 bits, 40 plus code. So we are using 12 bits. So that equals to 52 bits. So we need to calculate the message bits. Okay. So how do we calculate here? So here the code is of a variable length. It is having different lengths. But in the case of fixed size, we have same length. So that's why we have calculated it easily. But here it is of a different lengths. So how do we calculate here? So here 3 into 3. So totally 9. So 3 into 3 equals to 9. And so 5 into 2 bits. That is 10 bits. And so 11. 6 into 1, 2 bits, that is equals to 12 bits, and 4 into 2 bits, that is 8, and 2 into 3 bits, that is 6. So totally we have 9 plus 10 plus 12 plus 8 plus 6, that is 45 bits of, so 45 message bits we are transmitting. So totally message bits are 45 and table bits are 52. That means totally we are transmitting 97 bits of data through the network if you are using the variable size encoding scheme using the in the case of Huffman coding. So this is how we will solve the Huffman coding. Thanks for watching my video.